So let's start to talk about FlowViz, which is the final kind of section of the DataViz module. This is a big chunk of information, this particular lecture. It's also what I would classify as a non-trivial lecture, because when we get to numerical integration, there are some mathematics in there that they're not really difficult, but they're non-trivial as well. It's hard for me to say because I've seen it so many times and I've been around it for so long that I've lost track. But it's not very difficult at its basic, like what you are required to understand is not very difficult. However, it's very easy to make mistakes if you're working this out, numerical integration on an exam. So last time we gave an introduction to FlowViz on Monday, and today we are going to talk about some more advanced topics in FlowViz, direct FlowViz with arrow glyphs. That's not very difficult. But the numerical integration material is kind of non-trivial, I think. And then the streamline placement is kind of, I would say it's non-trivial. Yeah. So just as a heads up, if anybody brought coffee, nobody brought coffee. I started to do that when I was a master's student to stay awake during the lectures. I would always bring coffee because I was falling asleep. But the reason I was falling asleep was not because I was out partying every night and getting drunk. It was because I was studying and working. Anyways, so we'll talk firstly about so-called direct flow visualization with arrows or glyphs. So if we have vector data, the most naive way to depict a set of vectors is with an arrow, right? Just for every data sample, stick an arrow on there that's pointing in the same direction as the vector. That's the most naive thing you can do, right? And that's something we call direct flow visualization. And this is an example of just taking every data sample and sticking an arrow on there. Those are so-called normalized arrows. Does anybody know what that means, normalized arrows? I think some people here do know what that means, actually, but you're just too scared to say anything. Elisa, what do you think normalized arrows means? That's good. Nothing to do with the lecture, though. It's really a problem if I know your name, isn't it? The attendance register is being passed around. Everybody signed that? Anybody want to help Elisa out normalize arrows? I'll give you a hint. It's in the image. There's a hint in the image. Is it Emily? Yeah. Emily, what do you think?
Is it like they go
in a circle? Almost in a circle, kind of?
Like in a range.
The direction that they're pointing in corresponds to circular flow or a vortex. That's not necessarily normalized, what normalized means. So it's not a bad guess, though. Carlo?
Hasn't it got to do with the scale of the value of the standard deviation? So bring a more between 1 and -1 standard deviation and having with a comparable range of values.
You're close. You're making it too complicated, though. It just means all the arrows are the same length. Look, they're all the same length. They're uniform arrows. They've been normalized to unit length. In other words, they're all the same length. right? You could make them all a little bigger or all a little smaller. Another way of saying that is there's no information about velocity magnitude there. All the flow there looks like it's the same magnitude, the same speed. You cannot, that information has been removed, so only the direction is there. Right, so that's taking away a lot of information. And this is fine in 2 dimensions. It's very, very popular. It might be useful. There's also another thing going on here that is related to today's topic in the future slides. And that is when you are looking at those arrows, you are trying to figure out the way the flow moves from those arrows. Right? You're trying to understand, how does the flow move? You're trying to create paths that are longer than the arrows, like you're trying to actually integrate the flow in your mind. You want a path, right? But you don't want just a little arrow. Your mind is trying to derive paths. It's a little bit of a psychic exercise. So these are arrows that have different lengths to reflect the magnitude, and again, these are not the highest quality images, but you can still get some ideas, like some arrows are longer than others. And look, the arrows get very, very short here, so like they're reduced to just a dot, which is not very helpful in the low velocity magnitude areas. So that's why people use normalization sometimes, so that things don't get reduced to what happens when the velocity is 0, right? Like down here and so on. And here's with color. So you can encode magnitude with color. Right here, the dark blue color is low velocity magnitude, and then the red is high velocity magnitude. If we try to like use arrows in 3D, there's some challenges. Right, here are 2 arrows in 3D, but they look the same, but they're actually pointing in different directions. So this is the projection of that arrow onto the XY plane, for example, and the same with this arrow. And you can see when you project them down onto the plane, they're pointing in 2 directions, different directions. But you cannot see that just by looking at the blue arrow glyph all by itself. And that's the result of perspective shortening. That's what happens to the arrow, the image of the arrow, when it's projected from 3D to 2D. It gets shortened, unless it's exactly parallel to the view plane. That's not very likely. So 1D objects are difficult to perceive in 3D, and we can help by adding a 3D arrow with some shading. That does help. That definitely helps. And this is some more examples of using arrowglyphs to depict vector fields. This is a slice. Somebody has taken a slice through this 3D vector field and then placed arrows on the slice, 3D arrowglyphs, to show the flow. And you can see that the arrowglyphs are changing in their size. They're not all the same size. So some are very small, and then some are big. And the thickness is also changing of the arrowglyphs. Here are some more examples of arrowglyphs in 3D. They're not very good quality though, because these don't have shading. It's nice if they have shading. Here's another example of arrowglyphs combined with a surface. So like the surface of a terrain, for example, and the arrowglyphs pointing in the direction of the wind. It's not a very high quality image, but it's still, it's from 1996. But if you want to see like dynamic, very high quality images, you can look at the YouTube channel, which has a lot of, the DataViz YouTube channel has a lot of demos. Any questions about arrow glyphs? It's pretty straightforward. There's not a lot to discuss. There's nothing to compute really. So it's just a glyph. Okay, this is where it starts to get non-trivial. Anybody remember what a streamline is? I remember. Anybody? If you could just had to guess what a streamline is, could you just guess? We have mentioned it before. Anybody want to just guess what they think a streamline is? Should I call on somebody? Abdul, what do you think? What do you think a streamline is?
I think the probe that is tangled to the web.
Yeah, that's right. Why didn't you say anything?
I wasn't sure about it.
It's a curve that's always tangent to the vector field. Okay, what's tangent though?
I think maybe it's one. I'm sure.
Ah, I got ya. Anybody know what tangent is? You're supposed to know that word from mathematics, right?
The opposite of parallel, so always right.
It's projection of the plane, then above
You could one synonym-ish is aligned with, so it's the opposite of what you said. Yes, at the point of contact in mathematics, if you're tangent to a surface, if you're an edge that's tangent to a surface, it looks like this, right? It's aligned with the surface at the point of contact. That's right. So you can imagine a vector field, and you can imagine a curve which is navigating its way through the vector field and is always aligned with the vectors, the nearest or the most local vectors to the curve itself, along the curve. Yeah. That's what a streamline is. The other fun word is orthogonal or perpendicular, right? It's the opposite of perpendicular. This is perpendicular to the plane of the paper, the attendance register. Orthogonal means perpendicular, which is the opposite of tangent. You can think of some aquarium, and you can imagine dropping a massless particle into an aquarium, and the path that particle traverses through the aquarium is a streamline. That's kind of true. That's how you can think of it. Yeah. For the case of a streamline, it's only true for steady flow. In other words, the flow has to be time independent. It's a static flow. So the aquarium example is not perfect because an aquarium is normally time dependent.
So it's a current, basically. It's like a current.
Like a car?
A current.
A current, yes. Yes, if you were going to draw currents, curves of current that indicate current, those would be streamlines. That's right. And they're the third most popular flow viz. The most popular is just color mapping, color to velocity magnitude. The second most popular is arrow glyphs, and then the third most popular is streamlines. So tracing those curves through a vector field. And then the question is, how do you compute such a curve? How can you actually compute streamlines? input a vector field, you can output streamlines somehow. And that's what the topic of numerical integration is about, how to compute those curves or how to compute streamlines. We're not going to go deeply into the theory. Has anybody here taken calculus before? Nobody? I know Rodri did. But, so in some universities, you have to take a year of calculus as part of your computer science degree. Not at Swansea, but in calculus you would study things like derivatives and integration. And you would find out that velocity is a derivative quantity or a derived quantity. It's the displacement in x over displacement in time, or the displacement of position over time. That's what this is, the displacement in position over the displacement of time. You know that intuitively because you measure speed in meters per second, right? A distance, meters, divided by time, seconds, meters per second, right? So velocity is a derivative quantity. I'm not going to test you on the theory, by the way, but it's just kind of nice to have it there, like just in case you are interested and you want to have a little bit of a deeper understanding of the theory. So velocity is a derivative quantity, and to track the position of a particle as it traverses flow, we do the opposite of computing derivatives. The opposite of computing derivatives is called integration. And that's a subject you study in calculus, how do you integrate flow, right? So, in other words, you solve, a mathematician would say, how do you solve the equation for the position of the particle over time and space? And that's called integration. You use something called integration to solve for the position of the particle over time and space. You don't have, you didn't take calculus, so you didn't cover this topic of integration. But that's what this curve is. It's integration. It's an integral curve. So you're solving for a position over time. And actually, that corresponds to addition. This is a fancy symbol for, this is addition right here, this symbol, the plus sign. But this is also addition. It's a kind of addition. But it's continuous addition. This is discrete addition, and this is continuous addition. So normally when you add two numbers, you add 1 plus 2, and you get 3. That's discrete addition. You're adding one quantity, a discrete quantity, to another discrete quantity, and you get a third discrete quantity. Continuous addition, imagine saying, I want you to add 1 plus 2 plus all of the numbers in between, all of them. Like, how do you do that? That's continuous addition. That's integration. Anyways, that's just some theory. And integration in mathematics is approximated by a Taylor series expansion. That was really getting a little bit off the tangent. But you guys actually do study this. You've not had it said in this way, but you derive a discrete approximation to the integral, and it's a sum. And that's what we're going to talk about. And that is actually what you do in computer science. You derive an approximation to the analytical solution. In this integral symbol turns into a different symbol, and it turns into the capital sigma. So you all have seen the capital sigma symbol, which is the discrete version of the integration. anyways, it's some theory. You won't be tested on the theory. But it's good to it's good to know. It's not going to be on a pub quiz either, unfortunately. So imagine you wanted to track the position of a particle as it traverses some flow. How do you think you would do it? Imagine I just said you have to go do it and just figure out how to do it, how to approximate that. So you have a vector field in a 2D plane, and I give you a position, like a spot, a seed point, and I say, now draw the curve, the streamline that starts at this position. Just draw it. How would you do it?
Do you just follow the arrows?
Yeah, would you follow all of the arrows?
Well, you follow the one that goes after the one that you just said, which one you see in front of it, and you follow that.
You would start at the seed point and you would look for the nearest vectors. You'd say, like, what are the nearest vectors to this point? Maybe there's only one that's very close, but maybe there are 4 that are very close. You'd find the nearest n. Well, it depends on how accurate you want to be. Like, for the lowest accuracy, you would just find the nearest vector and then push the point in the direction of the nearest vector. Like, so if here's my point and here's the nearest vector, I would just take this point and push it a little bit in that direction, right? And then I would repeat the process. I would just have a for loop that says, okay, I'm here now. Where's the nearest vector? Okay, let's imagine the nearest vector is here. Now, which direction am I going to push my point in? This direction. And you just repeat. Every time you're in a position, you find the nearest vector, and you just push the point in the direction of that nearest vector. That's how you would do it intuitively, I think. Like, you would just guess, like, okay, I'm going to trace a curve. Now it's...
Some kind of symmetry break.
That's the nearest neighbor approximation, so to speak. If you want to get it more accurate, there are 2 ways to make it more accurate, and that is to look for example, the nearest 2 vectors. So imagine there's a vector here pointing in this direction and another vector here. Maybe it's pointing in a slightly different direction. You would average the 2, and then you'd get a vector and you'd push it in that direction. And you could keep going. You could say, okay, I'm going to look for the nearest 3 vectors and average those, or the nearest 4, or the nearest 5, or the nearest 6. And like one approximation would use a straightforward average, but the next higher approximation would use a weighted average. Like, so as the further away the vector gets, the less influence it has on that direction. So that's what we're going to talk about right now. It's got a very fancy name. It's called an Euler Integrator. But that is the basic idea behind the Euler Integrator. Just here's a position, evaluate the velocity, approximate the velocity at that position, and then move the particle a small distance in that direction. And the smaller that distance is, the higher the accuracy as well. Right? If you push it very far, it's less accurate. But that's called Euler integration. So evaluate the flow vector from its current streamline point for a small amount of time and therefore distance. So to compute points along a streamline, so this is the next point on a streamline, I take the current position, I evaluate the velocity at that current position, and I multiply it by a very small amount of time and distance, so it gets pushed to the next point. And that's called Euler integration. Right? That's a little preview. Here's where, here's an example of that. I'm going to show an example of computing a streamline, or we're not, I'm only going to go into details about computing a few steps, not like all of the steps, because it would take a long time. This is what computers are for. They're good at performing lots and lots of repetitive computation. So the input for this example is an analytical data vector field. And it's similar to Sally, actually. So Sally is an analytical vector field. This is another analytical vector field similar to Sally. So that means it's defined by an equation. And here it is. To get the x component of the velocity at any point, I just take the y coordinate and multiply it by -1. So for example, here, if I want the x component of the vector, I take the y coordinate. In this case, the y coordinate is -1. Everybody see that? 0, -1, that's the coordinate of that position. To get the x component of velocity, I multiply -1 by -1. So -1 by -1, and I get 1. That's the x components. What about the y components? To get the y component, I take the x coordinate and divide it by 2. So the x coordinate is 0 in this case. 0 divided by 2 is 0. Yes. So Vx is 1 and Vy is 0. That is the vector at this position. So it's just pointing that way. It's 1, 0. That's how you evaluate an analytical vector field. This is what the vector field looks like in this example. We could do another example. So for here, the x component is the y multiple. So y here is 1, right? Because this is 1 unit up. That's the y-axis. So 1 times -1 is -1. So the x component is this way. And then the y component, again, is x divided by 2. X divided by 2 is 0. 0 divided by 2, which is 0 again. So it's just pointing in the opposite direction. Does everybody understand this analytical vector field? And these are all arrows that are drawn. So this is the vector at this position, this is the vector at this position. You can see that they're going in a circle. Actually, you can't see that clearly here because the arrows are going in both directions, but actually what's happening is this is a circular flow. And as you get to the origin, it's 0, right? So it's 0 at the origin. And the further away you get from the origin, the greater the magnitude is. Right? And that's our input vector field. It's an analytical vector field. And now let's compute a streamline point using the Euler integrator. Right? So now the seed point, in this case, this is the seed point we're going to use for our streamline. And we just happened to choose that in a previous slide too. So just to make sure we're on the same page, to get the x component of the velocity, I've repeated the formula down here. It's just the y here is -1 times -1, which is 1. And then the x is 0 divided by 2, which is also 0. So we get that. So 1, 0, and that's what this is. So at the C point S naught, the velocity vector is 1, 0. That's what that is saying. And that's part of the Euler integrator, by the way. The Euler integrator says, take the current position, find out what the velocity, approximate the velocity here, and then push it a little bit in that direction to get the next C point. Now, how much do you push it by? In this case, we've set dt to a half. So it's actually a half times 1, and then a half times 0, which is a half 0. So the next position is right here on the streamline. Does the next slide show that? So that's the next position. So the first position is here, and the next position is here, half unit total in the positive x direction. And that's what this slide is showing. The previous position and the next position. And the numbers start to get more complicated, right? So the new point is the old point plus the vector at the origin times dt, which turns out to be 1/2 and multiplied minus 1. So that's the new point, because you're adding the points together. And if we want to get the current flow vector here, we need to do the same exercise. So what's the x component? Well, the x component is minus y. In this case, y is minus 1. So minus 1 times minus 1 is 1. And there's our 1. This is the velocity at the new point. Now what's x? That's the x component of the velocity. To get the y component of the velocity, we need to take x. X in this case is 1/2. Oh, I'm sorry. It's 1/2. So we've moved over a half. Right? So we divide a half by a half, and we get 1/4. So the y component of the velocity is 1/4. There it is. That's the y component of the velocity at this new point. And that's what this arrow is showing. So you have the half y going up, and then the full 1 of the x going in this direction. So when you add those two, you get a vector that looks like that. So this slide is really confusing, but actually what I'm saying is really simple. It's really, really simple. I'm making it more complicated than it really is. It's really simple. Right? All we're doing is adding numbers and multiplying numbers. That's it. But it is easy to make mistakes doing this. It's very easy. The reason, anybody know why it's a little bit trickier than what we're used to? I think it helps to know why. Anybody have a clue, like why it's a little bit trickier than what we all know how to add numbers, right? We're good at that. We're good at multiplying numbers together. And that's all we're doing here. But somehow it's a little bit tricky, isn't it? Somehow.
Is it because each result depends on the previous one?
Not necessarily, but maybe that adds a little bit of complexity. The complexity comes is because we're multiplying and adding vectors rather than scalars. We're used to adding and multiplying scalars together. But we're not used to adding and multiplying vectors together. That's what makes it a little bit confusing. We're just not used to that. We don't get much practice doing that. Maybe you've never even done it. Hopefully you have, but it's possible that you haven't. And that's what makes it a little bit non-trivial, because you have these two components you have to keep track of. The x, you're independently adding and multiplying the x component, and you're independently adding and multiplying the y components. You have to keep track and not mix those two things up. And so this is what happens, what it looks like when you compute the third point along this streamline. The fourth point, the numbers start to get ugly. The fifth point, the sixth point, right? Oh, this is the ninth point actually. The 14th point along this streamline, and then the 19th point along this streamline. So what happens is with these numbers, dt set to a half, you end up with this streamline that looks like this. Now remember, this is an approximation of the curve, which means there's some error. The perfect curve in this case is actually an ellipse. If there's no error, this would be an ellipse. It would start here, it would pass through here, and it would go right back to the origin. But there's some error here. And we can reduce the error by reducing the dt, or the amount of space between each sample. So instead of pushing it a half of a unit, we could push it a fourth of a unit. And that increases the accuracy. And the reason the accuracy increases is because the sampling rate increases. We went into this amazing explanation of the Nyquist limit, so the Nyquist theorem, one day, if anybody was here for that. And that's at what rate do you need to sample a signal in order to get an accurate reconstruction of that signal. And that, anyway, we went into a little bit of an explanation about that. That is true here. So the shorter dt is, the higher our sampling rate of the vector field, and the more accurate our reconstruction of the streamline is. The higher the sampling rate, the higher the accuracy. So this is what that streamline looks like if dt is set to a fourth. So 1/4 the length of an edge. So if this dt, this represents the distance dt equals 1. The first example used a half. This example is using a fourth of length of an edge. And the streamline is more accurate now. It's more accurate. But it requires more steps, right? 36 steps, whereas this one was 19. So it's just a trade-off between accuracy and the performance time, because it's going to take longer to compute 36 iterations than 19. And this is what it looks like when you just change dt. You use the same Euler integrator with different dt sizes. So this is a half, and that is this outer streamline. There's 1/4. That's this streamline. It's getting more accurate. This is 1/10, the orange one. And then the most accurate is 100th, and that approximates the solution the most accurately within a pixel, right? It's like you can't see if that's a perfect ellipse or not, but it is within a pixel. It's within a pixel of being exactly correct. So for our purposes, it's correct. Does that make sense to anybody? Hopefully. I know it is a tricky one, and it does come up on previous exams, this integration. And so I did do somebody asked in a previous exam if I could explain it again. And I took out a whiteboard and I drew every step, single step on the whiteboard, one step by step, so there's no way to get lost. It's impossible. And to see exactly how you could compute the next step on a streamline. So you can watch that again and look at that in case you got lost just now. And you can see how easy it is to make a mistake with this kind of thing. So don't panic if it wasn't 100% clear. Any questions about the integration so far, the Euler integration? It might look complicated on the slides, but actually it's not very complicated. If you think, oh, this is really just, exactly how I would do it, that's correct. It's just how you would do it if you were given this task, so to speak. This is some summary of the error. And before we finish, that was called a first order approximation. And there are better or higher order or more accurate approximations of a streamline. And the next most accurate, or the next most accurate approximation of a streamline is the Runge-Kutta integrator, which is more accurate than the Euler integrator. And that's because the Runge-Kutta integrator evaluates the velocity twice at two different positions. The Euler integrator only evaluates the velocity at one position, which is the seed position, and then approximates the flow there only. The idea behind the Runge-Kutta integrator is to look ahead. So look a half of a step ahead of where your seed point is, and then see what the velocity looks like if you're half of a step ahead. And then incorporate that into your average velocity. So you're sampling the vector field a little bit ahead of yourself on the streamline. So you do a half of an Euler step, evaluate the intermediate flow vector there, bring it or use it at the origin again, and then get a higher accuracy or higher order approximation of your next point on the streamline. So the next point on the streamline is this previous point plus the velocity evaluated twice. So the velocity at the seed position plus times the velocity at the seed position times dt divided by 2. And then you take that whole thing and you multiply it by dt. Yep. And that's what this is, an illustration of that idea. Remember, this is the same analytical vector field. With the Euler integrator, we just look at the velocity here and multiply the position by the velocity, and we get our next point. So our Euler integrator would predict the next point along this edge. The Runge-Kutta integrator says, okay, let's use this vector, but let's also use the vector, the preview vector, which is halfway along. And it turns out the preview vector points in this direction. So as soon as we're here, the velocity changes its direction. And we kind of average this one and this one together, and we get a more accurate position for our next point along the streamline. Right, instead of down here, it moves up, which is it more accurately approximates this ellipse. And we keep doing that over and over again. This is a comparison of the Euler integrator with dt set to 1/8 and Runge-Kutta 2 with the dt set to 1, which is much larger, very large distance compared to 1/8. And here's what the Euler integrator generates for streamline positions. And here's what the Runge-Kutta integrator generates for streamline positions. So it's more accurate, right? However, it takes longer to compute. Right? It's just a trade-off again between speed and accuracy. You can always increase the accuracy if you can take a hit on the performance and the speed. And there's another approximation that's even better, the Runge-Kutta Fourth Order integrator. So there are 4 vectors that are evaluated for every single step along the streamline. And then they're kind of averaged or weighted averaged together. So there's the original vector, the Runge-Kutta 2 vector, and then there's another Runge-Kutta 2 vector, and again, I don't have any nice drawings of that one though. And this is just a little bit more comparison of the different streamlines that are traced in this elliptical flow. So Runge-Kutta Fourth Order with dt set to 1/2, it's this green edge or the green curve, very accurate. The Euler integrator with the dt of 1/8 is less accurate, even though the dt is smaller. Runge-Kutta Second Order, where is that one? That one is... That's this one. Runge-Kutta Second Order, that's this one. Yeah. So it's the second least accurate in this example. This Euler, okay, this, I guess this Euler is hiding. Am I blind here? I think I'm blind. This is this Euler integrator here. That one and this one. And this one is the green dots along the middle. Yeah, they're overlapping. So the Runge-Kutta Second Order is along the inner ring here. And then this Euler is less accurate. And then the least accurate is this Euler, right? Which is on the outside. So a little bit confusing actually. Okay, so unless there are questions, if we will stop there for today. But I can say that this is a common question on past exams. Not necessarily this exam, but on past exams. Okay, you're all free for questions. Happy Friday.
Second year student that even project, but he can appreciate it.
Yeah, he seems very enthusiastic. It's unusual.
He did seem enthusiastic, and I'm afraid that he's gonna meet me at the worst time. He's got a very ambitious project. Very, very ambitious.
It's like a mirror image of yourself, isn't it?
detail.
Oh, good for good.
At least we won't let them use C++. Java. No exceptions this time.
Doesn't even know everything the same way I did.
I just have no.
Yeah, I did.